Hi everyone. In this tutorial I wanted to respond to a request that I read on osarc.org by Nigel, who wanted to find the area of inter-tenancy walls. So I looked up what inter-tenancy walls mean, and it looks like it is the walls that partition apartments from each other, and also maybe apartments from circulation, like corridors. So the idea is to find the total area of wall that separate these in between apartments. So let me just, I will show you the end result. I mean, you can see here that there's a number. This is 342. If this was in meters, this would be square meters. But let me hide and show you the actual walls at the end. So these are the actual walls that have been aggregated by topologic. And as you can see, it finds the walls that separate the apartments as well as the walls that separate the apartments from the circulation. If you don't want those walls that separate apartments from circulation, you can change the logic a little bit to filter them out. But for now, I'm just assuming that these are the walls that are needed. So how do we get those? So the first thing is that you will need a cell complex that has the apartments, the apartment number, like apartment 1, 2, 3, 4, 5, 6, 7, 8, saved in each room or each cell in that cell complex. So this is exactly what I have here. I have a file. I will probably share that. Well, not probably. I will share it. I will put it on osarc.org very soon. It's a JSON file that encodes the cell complex, and this cell complex has 49 cells, and each of these cells have a dictionary that has the value of APT, which is the apartment number, and they are grouped by apartment numbers. So you can see, for example, that these dark blue cells would have a dictionary with a apartment value of 1. And this other set of cells, 2, 3, 4, 5, 6, 7, 8, and then the corridor will have an apartment number, let's say, of 9. Or something just simply to be different. So this is already encoded. Usually if this data is coming from, let's say, a BIM system or Revit or something like that, this type of information will be available. So it's beyond the scope of this tutorial to show you how to encode that. But let's assume you have a cell complex that has the dictionaries already set in it. So the first thing is that we import those apartments. So we use topology by imported JSON. I used MK1. We have two variations of imported JSON. MK1 encodes the BREPs, the actual geometry, inside the same file. So you only need one file, not a folder structure. And MK2 separates the dictionaries from the actual BREPs. So in any case, this one here, topology by imported JSON, gives you a cell complex. So let me just simply show you that this is a cell complex. Sorry, it's going to take a little bit of time. So that's a cell complex. Great. So what do we do next? First thing we do is we draw the cells, and we draw them color-coded. So I get the subtopologies, I get the cells, and then I draw them normally. Just simply topology.geometry and then give a temporal viewer, and they get drawn. But in order to draw them by the correct colors, I get their dictionaries. So I get topology.dictionary of every cell, of every one of those 49 cells. And I find the value at key apartment. I already know that this is the key I use for the apartment number. So if I show you this, let me put a stethoscope on these 49 values. You'll notice that some are apartment 2, some are apartment 1, some are apartment 3, etc., so on and so forth. And this 9 here is the actual corridor. It's not an actual apartment, but I just gave it a 9 as a number. So based on these numbers, these 49 numbers, I create a color based on a value in a range. And I know that my apartments my apartment numbers vary between 1 and 9 because I have 9 different apartments. And I use a transparency of 0.5, and based on that I get 49 excuse me, colors. And of course, cells that have the same number will end up with the same color. So I feed that color into the color input here for the polygons. These are the, this is how you can specify the colors of entities. Excuse me. And that is what I get here. I get all the cells organized by color. So that is my cell complex. Great. So now we know we have at least done a sanity check that these apartments are organized correctly by color, and you can see them in plan here. Now obviously this is just a fake building of some sort. All right. So the idea now, of course, is to get the walls that separate apartments, but not the walls that separate rooms within the same apartment. So how do we do this? The easiest way is to, filter, first of all, by interior walls. We don't care about the exterior walls, so we just want interior walls. So we use the CellComplex.decompose, and we focus on the internal vertical faces. These are the 108 vertical faces. So if I draw these, and let me, sorry about that. Let me just make a copy of these and a copy of this one. Just to show you, I'm going to hide the whole cell complex, and just to show you those 108 faces, internal faces. So this is everything. You see, those are all the walls, all the interior walls. And the idea is, how do we filter for just the ones that separate the apartments? So let's go ahead and hide this. So how do we do this? The first thing we do is we get the cells that these walls separate. All right. So there is something called super topologies. Subtopologies are the ones that are below, like a cell has faces. So the faces are the subtopologies of the cell. But in topologic, you can also ask a face to give you its super topology, the one above it, the one that contains it, the one that uses it. And therefore you can ask a face to give you the cell. And I know that these interior faces will have exactly 2 cells each, one on each side of the wall. So I give the 108 faces, and you have to tell it which host topology this is part of. Like, you have to give it the cell complex. Super topologies require a host topology to kind of say which building are we talking about here. So you give it the cell complex, and you'll notice here that you have to flatten. This is F, so you have to flatten this for this to work. We'll look at that later on in later versions of topologic to make sure that we don't have to flatten lists. But for now, yeah, you have to flatten this. How do we flatten this? Basically, you go to sphere chalk, you click on socket menus here. Apologies for this. And then you choose socket menus, and that gives you a menu here where you can say flatten, simplify, wrap, unwrap, etc. Once we flatten this, now we have a list of 2 cells each. So if you want to take a look at this list, it will look like this. Stethoscope. So you'll notice that it is a list of lists, and every item has 2 cells in it, the rooms on each side. So I get the room at index 0, the first room, and the second room at index 1, but I operate on level 2 of this list, and it's intelligent enough to find out each one of those. And then what do? I get the dictionary of these rooms, so I now have 108 dictionaries for room 1 and for room 2, and then I get the value at the key, apartment, so now I have numbers, again 108 numbers each. So now I have these numbers, so you'll see them here. These are these numbers for these cells, and these are numbers for these cells. So these are the apartment numbers. And so what do I do very quickly? I subtract the two apartment numbers. Now, if the two apartment numbers are the same, the value, the subtraction will be 0. And if they're not the same, it will be either positive or negative, but at least not 0. So I get those subtraction numbers, and you'll notice some of them are 1s, some of them are 0s, etc. So based on whether it is a 0 or not 0, I look for the numbers that are not 0. Because if they are not 0, that means this wall is separating rooms that belong to different apartments. If they are within the same apartment, obviously the subtraction will be 0. So I use a Boolean logic or logic function called not equal, and I compare it to 0, and therefore I get a list of either false or true. This will give me a mask that I use to filter a list, and this is a technique that is well known in Sverchok and Grasshopper. You create a mask where it is a list that has the same length as the things that you want to filter, and sometimes it's false, sometimes it's true, and it will pick out only the items that have a true in them. So you can filter by that mask. So there is something called list mask out, and what you do is you give it the data and you give it the mask. So you remember we had 108 faces from here. Those are our 108 faces, and we are filtering them by the two cells that are adjoining. If they are the same, we filter that out, and if they're not the same, we keep them. So let's go ahead and see what the result is. So now that we have filtered these 108 according to this mask, we get a result of 36 faces. And these are the 36 faces. So let's go ahead and draw them. So I'm just going to highlight this. And these are the resulting 36 faces. Okay, so now Nigel on OSR also wanted the areas because he wants to do some analysis and calculations. So let's add up the areas of these faces. So we have something called face.area. And because we are giving it 36 faces, we're going to get 36 areas out. So we sum them up, we add them all up, and we get the number 342. And we just simply now draw it, and that's why you see the number 342 here. That is it really for this tutorial. I will put this Blender file and the JSON file up and this video so that you can try it for yourself. I hope you enjoyed it. Thank you.